questions 21 through 25 on the 2010 grade 12 AMC 12B. Let a be greater than 0 and let p to the x be a polynomial with integer coefficients such that p at 1 equals p at 3 equals p at 5 equals p at 7 equals a. And p at 2, p at 4, p at 6, p at 8 all equal negative a. What is the smallest possible value of a? Let a be greater than 0. Let p at x be a polynomial with integer coefficients such that p at 1 equals p at 3 equals p at 5 equals p at 7 equals a, and p at 2, 4, 6, and 8 equals negative a. What is the smallest possible value for that a? Okay, where do we go from here? Well, one thing I immediately notice is that if you were to take each of these, right, for example, p at 1 is equal to a, and if you rearrange that, it just means that p at 1 minus a is equal to 0, correct? And very similarly, you can do that for every one of those. P at 3 minus a is equal to 0, p at 5 minus a is equal to 0, and p at 7 minus a is equal to 0. All right? So what we can immediately do is introduce a polynomial. Let's call it r at x, and we'll call that p at x minus a. And since p at 1, 3, 5, 7 minus a equals 0, that means that this polynomial has roots when x is equal to 1, 3, 5, and 7. So, since those are the roots, we can write it as follows: x minus 1, x minus 3, x minus 5, x minus 7. Correct? Now, those are not all the roots. I don't know what all the roots are. I just know some of the roots. So I can't just leave it at that. I also have to tag on a q at x, where q at x represents the remainder of the polynomial. I have no idea what that is. So keep that in mind. All right, where do we go from here? Well, we know that this r at x is p at x minus a. So let's just put that back in, because that's going to be very helpful for us, and the rest remains the same. Okay, now we're going to have some fun. Now is where we substitute these guys. P at 2, P at 4, 6, and 8. So when we do, we will get some interesting results. First, let's do P at 2. If we substitute 2 for x, we get P at 2 minus a is equal to 2 minus 1 times 2 minus 3 times 2 minus 5 times 2 minus 7. And then we have q at 2. And that is equal to minus a, correct? So we have minus a. But I'd like to actually get a numerical value, so I will. When you do all this, numbers, whatever, you get minus 15 q at 2 is equal to minus a. But be a little careful, because remember, p at 2 is minus a, but we are actually subtracting another minus a. So this is actually minus a minus a. So it's actually minus 2a. Not that it makes a big difference, but just to be complete and accurate. Now we do the exact same thing for p at 4. P at 4 minus a, we'll substitute that in. And if you do the math here, you get 9q4 is equal to minus 2a. And then, of course, we'll do the exact same thing for p at 6 and p at 8. And that is again going to be minus 15q6 is equal to minus 2a. And then finally, we do p at 8 in the exact same way, minus a, using this same equation up here. And if you do the math there, you get 105 Q8 is equal to minus 2A. All right. So what did we get here? We have a whole bunch of formulas. We got the first one, which is minus 15 Q2 is equal to minus 2A. Then we got 9 Q4 is equal to minus 2A. Minus 15 Q6 is equal to minus 2A. And 105 Q8 is equal to minus 2A. So all of these are equivalent. Now, for all of those to be equivalent, that means that these guys are all equivalent. Correct? So to figure out A, we really have to figure out the lowest common multiple of these numbers, which are 15, 9, 15, and 105. That's what this boils down to. Well, 15 is 3 times 5, 9 is 3 times 3, 15, of course, again, is 3 times 5, and 105 is 3 times 5 times 7. So the LCM, 3, we would have to use it twice, since it appears twice. We have to use it as maximum amount of time it appears. The 5 only appears once, and the 7 only appears once. So that is the LCM, 3 times 3 times 5 times 7. And if you do that, that is 315. And that is the minimum, because A is going to be something times 315, 315n perhaps. And this is minimized when n is equal to 1. And that, of course, gives a value of 315. So the answer to number 25 is B. Let ABCD be a cyclic quadrilateral. The side lengths of ABCD are distinct integers less than 15, such that BC times CD equals AB times DA. What is the largest possible value of BD? Let's first draw a quadrilateral. Anything is sufficient for now, since we don't really know what it looks like. So here's a quadrilateral. And I will label it ABCD. And then let's just give the side lengths some value. So I'll call this A, this B, this C, and this D. And then, of course, they have drawn this diagonal called BD. And they've also told us that it's cyclic. And what that means, cyclic, is that if you have an angle, this angle right here, angle A, and if you add it to that angle, the opposite angle, which is angle C, it equals 180. So that comes in handy because that means angle C is 180 minus A. And the way it comes in handy usually is when you take a trigonometry such as cos, and you take the cos of, say, C. You can write that as the cos of 180 minus A, since they are equal. And that can be changed because cos of 180 minus A is the same as the negative cos of A. So that kind of a substitution is possible with cyclic quadrilaterals, since their angles have this property that opposite angles add up to 180. So now, on this cyclic quadrilateral, we are going to use the law of cosines. And in particular, to talk about BD, this length right here that they have asked us for in the question stem. So let's first do this triangle right here, that one, using the law of cosines. BD squared will be A squared plus D squared minus 2AD cos of A. And then same kind of story, but we'll use that triangle this time. And that gives me BD squared is equal to B squared plus C squared minus 2BC cos C. Now, just like I did over here, cos of C is negative A, I'm going to put that here, because that makes it similar to that one. And if I do that, I get bd squared is equal to b squared plus c squared. Now cos of c is negative cos of a, so this becomes plus 2bc cos of a. And then what about this guy up here? Anything we can do? And the answer is yes, right there. That is very helpful to us because that allows me to substitute this guy right here to make it similar again. If we look at this equation that they gave us in the question and apply my lettering, let's see, it becomes b times dA bc is equal to ABA and dA is d, like that. So this AD equals BC, so that means instead of this AD here, I can just put BC. So that means this becomes BD squared is A squared plus D squared, but instead of minus 2AD, I can put minus 2BC. And there we go. This equation and this equation are now very similar. I'll call this equation 1, and I'll call this equation 2. And now what I'm going to do is add them. 1 plus 2, like that. If I do, the left side becomes just 2bd squared, and the right side, conveniently, these guys cancel out, which is obviously very helpful for us. And all you're left with is just a squared plus b squared plus c squared plus d squared. Okay? At this point of the question, we have to utilize this piece of information that the side lengths are all distinct, so they're all different, and they're all less than 15. So we have a task of maximizing this with 4 integers that are all less than 15. And that is what we are going to proceed with. So then at this point, this is just plug and play. So you say, okay, well, all of these are going to be less than 15, and they're all distinct, meaning they're all different. So let's see here. What about if A is 14? And also, we can utilize this piece of information that BC is equal to AD. That will help us too. So I'll put that over here. If A is 14, then that means that over on this side, we got to have something that is a factor of 14. So, I don't know, let's say B is 7. If that is the case, then I can choose a value of B being 7 and A being 14. But what about C and D? Well, obviously, C has to be twice of D in order for this to work. So since I'm trying to choose pretty big numbers that are less than 15, I'll choose C equal to 12. That's about as large as I can get to be able to make D 6. If D is 6, then 12 is the maximum. Because if I chose anything larger than 12, it wouldn't be able to be cut in half exactly and still be an integer. 13 wouldn't do it. And 14, I can't choose because I've already chosen 14 and all 4 of these are distinct. So if I use this, C is 12 and D is 6, what do I get? Well, I get 2bd squared is equal to 14 squared plus 7 squared plus 12 squared plus 6 squared. And that is 196 plus 49 plus 144 plus 36. And that totals 425. So therefore BD is going to be 425 divided by 2, and then all under the square root sign. So number 22, the answer is D. Monic quadratic polynomials p at x and q at x have the property that p at q at x has zeros at x equals negative 23, negative 21, negative 17, and negative 15. And q at p at x has zeros at x equals negative 59, negative 57, negative 51, and negative 41. What is the sum of the minimum possible values of p at x and q at x? We will write p at x and q at x in the form that clearly shows us the minimum, and that is in the form that shows the vertex. And you all remember this form where the vertex is going to be A and minus B. So when x is equal to A, we have the value of P at x is equal to minus B, and that's the minimum value. So in a very similar way, we will let Q at x be a polynomial in a similar form. So we'll let it be x minus c squared minus d. And the vertex here, of course, is c minus d. And what that means is that when x equals c, Q at x is equal to minus d. And that is the minimum, because these are parabolas that point upward like this, and the minimum value will be right there. Now, our task is to find the sum. So that I'll write up here. The sum, obviously, will be this plus this. So it'll just be minus b minus d. You're adding those two together. So if I can find the numerical value of b and the numerical value of d, I'm done with the question. But obviously, it's not as simple as that. It's going to take a little bit of work here. So here we go. Now, if we were to expand these out, these guys right here, I'll just quickly write what they will look like. So P at x is this, and Q at x is that, and we'll be able to use that later on. Now, let's start talking about the roots. If you notice that P at x has roots as follows, if you were to set it equal to 0, like this, 0 is equal to x minus a squared minus b, and then we try to isolate for x. B comes over here, and then take the square root, and you get negative b plus or minus, and then the a comes over here. So those are the roots. X is equal to a plus or minus root b. So let's move this up. Now, the roots of p at q at x are also the roots of q at x. And those roots, of course, like I had just calculated, are a plus or minus b. So if we look at this from the perspective of these equations that I wrote up here, the sum of the roots of q at x, where q at x is this, we can find very quickly using Vieta's formula. If you remember Vieta's formula, the sum of the roots are minus b over a, right? So looking at this equation up here, minus b over a would just be this negative over 1. So that's 2. So I'll just write that out. Using Vieta's formula, the sum of the roots of q at x is 2c, and that's directly from that equation. And then therefore the sum of the roots of p at q at x is going to be 4c, since you're doubling that. And then now we incorporate all the roots, and those roots they have given us right here. These guys are the roots of p at q at x. So those roots are going to be minus 23, if we add them all up, minus 21, minus 17, and minus 15, and they all equal 4c. And this becomes minus 76 is equal to 4c, and therefore c is equal to minus 19. So that means my q at x formula, if you go back and look at this guy right here, since I have figured out c, I can just sub that in, and I get x plus 19 squared minus d. And we have to now do the exact same thing for this scenario right here, and this scenario, combining those to figure out the numerical values here. So, in a very similar way, q at x, which is obviously equal to x minus c squared minus d, we can figure out the roots here in terms of our letters. by setting it equal to 0. We're doing pretty much the exact same thing we did over here. And let's see what we get. This becomes d. When you bring it over, of course, you take the square root plus or minus, and that's going to be x minus c, and therefore x is going to be c plus or minus the square root of d. Okay? And in a very similar way, the roots of q at p at x are the roots of p at x. And very similarly, using Vieta's formula, we can find the sum of the roots of p at x very quickly. And of course, we're looking at this guy right here. Vieta's formula applied to p at x is as follows. The sum of the roots are minus b over a, right? And in our case, my b is minus 2a. So that's going to be here, minus 2a. And my a is the coefficient here, which is just 1. So this just becomes 2a. And therefore, the sum of the roots of q at p at x is 4a. And then now we go back and we look at what are the roots of q at p at x. It's these four guys. So we have to add them up and apply our Vieta's formula in a very similar way as we did before. So this time it's minus 59. Those four roots added together, minus 57, minus 51, minus 49 is equal to 4a. And therefore, 4a is equal to minus 216. And therefore, minus 54 is equal to a. So our p at x, we have at least part of it. It's x plus 54 squared minus b. So now we have to figure out b and d using this information. So if you remember, the roots before were x is c plus or minus root d, and the roots that I got over here were a plus or minus b square root. Now we have the formula that shows us the numerical values for a or b, so this just becomes x is equal to minus 54 plus or minus the square root of b, and this becomes x is equal to minus 19 plus or minus the square root of d. Now to figure out the actual numerical values of b and d, we have to go back and look at the roots of any of these. So I'll just choose the roots of p at q at x, and those are given in the question. If I go back and use those, I can substitute them in and try to figure this out. So I'll use these two. I think that's sufficient. Couple roots of p at q at x to figure out numerical values for b and d. So I can substitute, let's say, q at negative 23, and that's going to be equal to one of these, so I'll set it equal to minus 54 plus root b. And then the other one I can choose, let's say, minus 21, and set that to minus 54 minus b. And this is possible since they tell you in the question that q at x is monic. So let's do this here. And remember, here's the formula for q at x. So that's what I'm going to substitute minus 23 in. Minus 23 goes right here. And if I do, I get minus 23 plus 19, which is minus 4. And then if I square it, it becomes 16 minus d. And that is equal to minus 54 plus root b. In a very similar way, if I put in minus 21 into this equation, then I get 2 minus 2 squared, so that's going to be 4 minus d is equal to minus 54 minus root b. Now at this point, we got two equations, two variables. We can now solve this. So I can, in any way I want. So the first thing I'll do here, to get rid of these guys, I'll just add them. So add the left side and the right side. You get 20 minus 2d is equal to minus 108. And therefore 2d is equal to 128. And therefore d is 64. And then to get the value of b is just substituted back into any of these. So for example, if I put 16 minus d A is equal to minus 54 plus root b. 16 minus d, d is minus 64. So 16 minus 64, and then bring the 54 over. That will be root b. So that looks like it will be positive 6 is root b, and therefore b, if you take the square of both sides, is 36. So there we go. We got actual numerical values for b and d. And if you go back to the very beginning of the question, we have to add up just minus b and minus d. Well, minus b and minus d are not a problem. B we had gotten to be 36, so this is minus 36. D we had calculated to be 64. So minus 36 minus 64 is minus 100. So therefore, number 23, the answer is A. The set of real numbers x for which 1 over x minus 2009 plus 1 over x minus 2010 plus 1 over x minus 2011 is greater than or equal to 1 is the union of the intervals of the form x is greater than a but less than or equal to b. What is the sum of the lengths of these intervals? Let us first explain this question with the actual diagram of this inequality. And here is that diagram, and I will try my best to carefully explain what is happening. First and foremost, this 1 is represented by this line right there, that blue line. And this 1 over x minus 2009 and this have certain conditions with regard to the denominator. For example, x cannot be 2009, because if it did, it would be undefined. And similarly, it cannot be 2010 and it cannot be 2011. Okay? Now, to make our lives simple, we make a substitution. And the substitution is as follows, and this is perfectly allowable, is we let any variable, I'll just choose p, equal to x minus 2010. And if you do that, this equation now becomes 1 over p plus 1 plus 1 over p plus 1 over p minus 1, and that is greater than or equal to 1. And the good news is that if you do this, the intervals don't change. The solutions of this will not affect the intervals. So now let's talk about this. This graph that is right here is designed for this right here. It just makes it a little bit simpler when you're dealing with ones and negative ones rather than bigger numbers like that. Okay, so this 1 is represented by this horizontal line. And then now, very similar to the original one, we have 3 lines that represent where this is undefined. And as you are well aware, those are known as asymptotes. And those asymptotes, in this particular case, will be -1, 0, and 1. For those values of p, these would be undefined. So the graph can never touch those, never hit those. They can come close, but it can never hit those. And those are right here. This is -1, obviously. 0 is obviously here. And here's 1. As you can clearly see, the graph comes very close, but it never touches it. And then these curves that are in red, this one, this one, this one, and that one, they are basically representing the values that are allowed in this inequality. Now, what we have to figure out is, when is this graph greater than or equal to 1? Well, it's greater than or equal to 1 when it's above this line. So obviously here, here, and here up until that point. So that's it. Those are the points. And what are the intervals? Well, remember, it approaches -1, so it's from -1 right here to this point, and I don't know that point, so I'm going to just call it A. Then it's from 0 right here, so I'll just call that 0, to this point. I don't know that point, I'll call it B. And then it's from 1, so I'll just call that 1, to this point, which I don't know, so I'll call it C. In those intervals that are all of this form, this graph is above 1, and 1 is represented by that horizontal line. So my intervals are x is greater than -1, but less than or equal to a. My second interval is x is greater than 0, less than or equal to b. And my third interval is x is greater than 1, is less than or equal to c. Okay, those are my intervals. What they're asking is for us to add up those intervals. So that first interval is from there to there, that second interval is from there to there, and that third interval is from there to there. They want you to add them. Okay, I can add them actually just with my variables. Adding these intervals, you get the following. The first interval right here is equivalent to c minus 1. This interval right here is equivalent to b minus 0. And this interval right here is equivalent, in terms of a positive length, to 1 plus a. This represents the sum of those three intervals. If you add these up, you'll notice something interesting happen, that the -1 and the 1 cancel, and this just becomes a plus b plus c. And that is very interesting because a, b, and c represent what you can consider sort of the roots of this equation. So really, this is the sum of the roots. So if I can find the sum of the roots of this equation, that's it. I'm done. So that's what we're going to concentrate on. And I think that is really, in my humble opinion, challenging. It's a great question. So now let's concentrate on making this into one single equation, and then we will find the roots, probably using Vieta's formula. So here we go. All right, so here we go. We now have to obviously combine all this. This is going to be a fraction, so the denominator, this is my common denominator. On the top here, this is going to be p times p minus 1. This will be p plus 1 times p minus 1. And this one will be p plus 1 times p, like that. And that's greater than or equal to 1. So expanding this, we get p squared minus p plus p squared minus 1 plus p squared plus 1. And then we can cross multiply and bring that over. And that will be p plus 1, p minus 1, and p, like that. Let's see here. On the left side, looks like we get 3p squared, and then that's it. This should be p, sorry. So those p's cancel. And when they do, you just get minus 1. On this side, let's just expand this. So this will be p squared minus 1, and then multiplying by p. So this will be p to the third minus p, and this is p squared minus 1. And then put everything on one side, so we get minus p to the third, and plus 3p squared plus p minus 1 is greater than or equal to 0. So at this point, we have to look at this, and this is much simpler because now we can use Vieta's formula. And I'm sure you know that formula, but just in case you didn't, it's a squared, or a to the third in this case, because we have a third degree polynomial, plus 3, well, I'm substituting in numbers, but actually we have to substitute in letters, bx squared plus cx plus d. If you have a polynomial of that form and you're trying to find the roots, Vieta's formula says that the sum of the roots are going to be minus b over a. So in this polynomial, our minus b over a, well, is going to be minus b in this case is 3, and our a in this case is -1. So it becomes minus 3 over -1, which is 3. And 3 is the sum of the roots, but the sum of the roots represents the length of those intervals, all added up. So 3 is the sum of the roots, which represents the length, the sum of the lengths of those intervals, and therefore that is the answer to the question. And you'll notice what's interesting about this is that even though we made the substitution, it did not affect the sum of the lengths of the intervals. And I think that substitution obviously makes the mathematics a lot easier. And if you get the same answer using it, then it's definitely worth making that substitution. So number 24, the answer is C. For every integer n greater than or equal to 2, let pow n be the largest power of the largest prime that divides n. For example, pow of 144, which is pow of 2 to the 4 times 3 to the 2, is 3 to the 2. What is the largest integer m such that 2010 to the power of m divides the product of pow n from n equals 2 to 5,300? This is a very, very interesting question. It's a very good question, and I'll try my best to explain it. So first and foremost, do you know what this means? Most likely, if you're in grade 12, it just means you're multiplying this guy for every value of n from n2 to 5,300. So it's like a continuous multiplication. And what they're asking in the question is that if you do that, you take this, it's going to look like a pi when I write it, but it's not. It's a different symbol. So if you do this whole thing, and it's obviously a very, very big number, and then you divide by this 2010 to the m, what's the largest possible value you can have for m such that this is an integer? Because this statement, such that 2010 m divides this, means that when you do the division, it turns out to be some integer. So I'll just write I for integer. So how do we approach this? Well, the first thing I want to do is break up this 2010. Instead of writing 2010 to the m, I want to break it up into its prime factors. And the prime factors of 2010 are 2, 3, 5, and 67. And therefore each of them will be to the power of m when you break it up like that. And of course this is a multiplication. Now, this might take a little bit of practice. On a math contest, you've got 3 minutes. So the challenge of this question, in my opinion, is not the difficulty of the question, but the time constraint. If I sent you home for the weekend and said, hey, take this question home, I guarantee you'd be able to do it because you've got, whatever amount of time you need. But you got 3 minutes on a math contest. That's the challenge, because otherwise it's actually a very cool little question. It's not really that difficult. As you can see, they've even given you an example. So what we will do is only concentrate on this one, 67. Now you might say, well, how do you know? How do you know 67 is the one you have to concentrate on? Why aren't you going to concentrate on 2 or 3 or 5? And that's a debate I've read on the internet. It's a great debate. And the answer is because you don't have time. That's the actual answer to that question, because 67 is way larger than these numbers, and I'm pretty much certain that there's going to be a whole lot of 2s and 3s and 5s in this whole big thing, but there's not going to be as many 67s. So if 67 divides this, then I'm pretty sure that is going to be the largest value of m. So here we go. I'm going to just write out 67 in terms of this product. So we've got the pow of 67. If n was 67, then it would become 67, right? Because we're basically going by that definition right there. You take any number, you break it up into its prime factors, and then you extract from it the largest one. So in 67, that's just 1 times 67. The largest prime factor obviously is 67. So pow of 67 becomes just 67. Okay? And in a very similar way, you can do that for any multiple of 67. So for example, if you have pow of 67 times 2, that, according to this definition, is also going to be 67, since you're taking the largest prime. And very similarly, the same story holds true for any multiple of 67, with a few exceptions. So I'm not going to obviously write them all out, but I'll just write ... and then I'll write the exceptions. So first and foremost, we're going to get all the way down to 67 times 66. All of these will have 67 as its largest prime until we get to pow of 67 times 67. This one, when you extract the prime, you're extracting 67 squared. Okay? So that is a little unique. So because it's unique, I'm going to put a little underline like that. And then you just keep going, powers of 67. The next one is 67 times 68, like that. And I'll write out all of them until the very end. And that's it. That's to the very end. And you say, well, how do you know it ends there? Well, because 67 times 79 is 5,293. And we're only going up until 5300. If you do 67 times 80, which would be the next one, that's 5,360. And that's greater than where we're going up to. So this is the last one that involves 67. Now let's talk about this. This is where the question gets interesting. For each of these, right, we're only going to get 67. And therefore, when we get 67, we only get 1 as the exponent. Okay? All of these exponents are going to be added up, and that is what they're asking for. This one also gives 1 as the exponent for 67. This is 1, this is 1. This is 2, though. And you see the answer choices are very similar, so they're making that assumption that you're going to miss this guy. Okay, let's keep going. This gives you 1. This gives you 1. This gives you 1. Now, this is the tricky one. Why? Because 71 is a prime. So the pow of 67 times 71 will not be 67. It will be 71. So you don't get any exponent for 67. You see that there? And then this one will give you 1 because 72 is not prime, but 73 is a prime. So the pow of that will give you 73. This one will give you 1. This one will give you 1. 76 will also give you 1. 1, 1, and this one, 79, is a prime, so this one will give you 79. Now for all of these, I didn't write the 67, right? It's really 67 to the power of 1. I just wrote the exponent. So our task now is to add up all of the exponents. Okay, no problem. From the very first one up until this one, there's 66, correct? I didn't write them all in, but we have 67 times 1, 67 times 2, 67 times 3, all the way till 67 times 66. And each of those give an exponent of 1. So we got 66, these guys right here. Those give 66 in terms of when you add up the exponents of 67 to the power of 1, 66 times. This one here gives you 2. And then we're going to add these manually. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I got 9 there. So 9 plus 2, which is 11, plus 66, which is 77. That is going to be up here. If you did this whole thing, it would be 67 to the power of 77. And therefore, the largest possible m in the denominator is 77. Because if it's anything greater than 77, this will not be an integer. Right? So I hope that makes sense. It's a really good question. Practice it. I hope I have explained it the best I can. If you're still unclear, take it home for the weekend. Spend more than 3 minutes on it. And I hope you come to the same conclusion. So number 25, the answer is D.